Now we're going to talk about how to estimate a population mean when we don't know the value of the population standard deviation. So here we're going to calculate the population mean when sigma is not known. So here sigma is not known, okay? So let's first start by talking about the student t distribution. If a population has a normal distribution, then the distribution of t equals x bar minus mu over s divided by the square root of n. Notice this right here. We have not sigma over the square root of n, but s over the square root of n. That's a distinction between this and the z-score. When we're doing the z-score with the central limit theorem, that value is not s, but sigma. But we don't know sigma, so we can't use the population standard deviation to calculate t. We have to use the only thing we have, which is a sample standard deviation. So if we don't know the population standard deviation, we have to resort to the sample standard deviation. And if we're using the sample standard deviation, we have to use the t distribution. We cannot use the z distribution. So this is a student t distribution for all samples of size n. A student t distribution is often referred to just as the t distribution. So if you hear me saying t distribution, this is the one I'm talking about. Now we have another definition. The definition is the number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all the data values. The number of degrees of freedom is often abbreviated df. So if you see the abbreviation df, we're talking about degrees of freedom. That definition, not extremely important. This formula is extremely important. This is how we're going to find our degrees of freedom. So more important than what the degrees of freedom are in this case is the formula for actually finding the degrees of freedom, because we're going to have to use that in making our intervals. All right. So here it is. This is how we make a confidence interval estimate. Okay. This is how we're going to make a confidence interval estimate for a population mean when we know the value of sigma, all right? So if we know the value of sigma, here's what we're going to do. So the objective is to construct a confidence interval used to estimate a population mean, just like the objective was when we knew sigma. Only distinction once again here, sigma is not known. All right, now all the notation here is the same except for this notation right here. And this one right here used to be sigma, but now we don't know sigma, so we can only use s, the sample standard deviation. All right, let's talk about this one, the critical t value. The critical t value is the value separating an area of alpha over 2 in the right tail of the t distribution. So this is not the standard normal distribution we're talking about. This is the student t distribution. Down here, table A3 in the back of your book has a list of values for critical values for the student t distribution. So here's how we're going to find our critical t scores. We're looking for the area in the right tail. See, notice critical value separating the area of alpha over 2 in the right tail of the t distribution. So we're only in one tail. So whenever we're finding a critical value, we're going to be looking at this row up here that has areas in one tail. So we're going to be looking at this row which has the areas that are in one tail. It doesn't matter that it only says one tail because we're looking at the right tail, which is only one of them. So we're looking at this row here. What we're going to do is we're going to look for our value of alpha over 2. We're going to look for our value alpha over 2 in this top row. So we can only do certain values for alpha over 2. This value for alpha over 2, this is a value for alpha over 2, and we have these other 3 values for alpha over 2. So with this table, we can only find 3 values of alpha over 2, so we can only find critical values for the t distribution if we have one of these standard areas, either 0.005, 0.01, 0.025, 0.05, or 0.10. So those are the only alpha over 2s that we can actually find critical values for using this table. This mouse is acting kind of strange today. All right, so that's the distinction between this section and the section where we were calculating confidence intervals with sigma known. All right, so the requirements here are also different. So let's take a look at the requirements. In this case, remember when we were doing it with sigma known, we had three requirements. The first requirement was the same. The sample is a simple random sample. The second requirement, if we knew sigma, was that we actually knew sigma. But we don't know sigma in this case because we're doing this with sigma not known, so that requirement is thrown out the window. We don't have to know sigma if we're going to use the methods of this section. But this criteria still has to be met. Either the sample is from a normally distributed population or the sample size is large enough. And by large enough, we say 30 is a large enough size. So anything greater than 30 is going to be what we consider a large enough sample. We're still doing the same things though. To calculate the confidence interval, we're still going to take our point interval, our point estimate x bar, and add and subtract the value of e, the margin of error. The only difference, now the margin of error is going to be calculated differently. Now, remember in the last section we looked at, the margin of error, when we knew sigma was equal to the z of alpha over 2, we used the z-score instead of a t-score. And instead of s, we used sigma because we knew sigma, and it was over the square root of n. Well, this is pretty much the same thing, except we replace the z-score with the t value, the critical t value, and we replace sigma with s. And now we have additional information. We need to know what the degrees of freedom are. So we need to know the degrees of freedom, which are n minus 1. So now we're going to calculate our margin of error slightly differently. We're not using this formula anymore with the z-score and the population standard deviation anymore. We're using this new formula that has a t-score and a sample standard deviation. All right, so let's see. Let's look at some example problems here. Okay, this thing is acting screwy. Well, here's how we actually decide whether we're going to use a T or a Z. So this table is actually in your book. This table is table 7.6, and it's how to choose between Z and T. And this is going to help us to do these problems right here. So we're going to choose whether or not we're going to use Z or T. And then if we're going to use Z, we'll find the critical Z. And if we're going to use T, we're going to find the critical T using table A3 that's right above that flow chart right here. So if we use Z, we're going to use, if we have to find a critical Z, we're going to use the calculator. If we have to find a critical T, we're going to use table A3. So using the correct distribution. In exercises 5 through 12, assume that we want to construct a confidence interval using the given confidence level. Do one of the following as appropriate. So we're either going to A, find the critical Z value. Well, we can only find the critical Z value when we know sigma and those other requirements are also met. Part B, find the critical T value. Well, even if we don't know sigma, we can still find a critical T value as long as it's a simple random sample and either it's a normal distribution or the sample size is larger than 30. And C, this can also happen. We state that neither the normal distribution nor the T distribution applies. If we don't meet any of the criteria for the normal distribution, the Z distribution, and we also don't meet any of the criteria for the T distribution, we can use neither one. So there are three choices here. So let's take a look at number 6. Oops. Let's take a look here at number 6. So in number 6, scroll back down. In number 6, it says we have a 99% confidence level. So we have a couple pieces of information here. We have the confidence level to be 99%. So we know the confidence level is 0.99, which means we have alpha, which is 1 minus the confidence level. So that's 0.01, which means we also know alpha over 2. So we're looking for either the Z of alpha over 2 or the T of alpha over 2, or maybe neither one. But alpha over 2 in this case is going to be 0.005. So right there, just by being given the confidence level, we can assume all of those things. And it says it's 25. So I have the sample size is 25. Remember, a large enough sample needs to be size 30. So unless this thing is normally distributed, we cannot use Z or T. Here we see that sigma is known. Because I know sigma, if I am going to use z or t, it would be the z-score that I would use, because you use the z-score when you know sigma. And then it says here, the population appears to be normally distributed. Well, we have to meet two criteria, or as long as sigma is known, we have to meet two other criteria in order to be able to use the z-score. The two criteria were either the the first criteria was that it's a simple random sample. We can assume that all these samples are simple random samples. The second criteria was to meet, the second requirement was we had to meet one of two conditions. Now, those conditions were: one, either the sample size was large enough, and we know in this case the sample size is not large enough, but as long as this population is normally distributed, we can still use z. So in this case, we're going to calculate a critical z-score. So in this case, we're looking for a z of alpha over 2. So we're going to find the z of alpha over 2. And let's see how we do that. Well, we have alpha over 2 as 0.005. To find the z of alpha over 2, once again, we go to our TI 83 calculator. We turn it on, and let's see. We do second distributions, and we want the inverse normal distribution number 3. Oops, that's the chi-squared. So second distributions, and once again we want number 3, the inverse normal distribution. And what we're going to plug in here is we're going to actually plug in 1 minus alpha over 2, which is 1 minus 0.005. So 1 minus 0.005 will give us our critical z, and that is equal to 2.58. We've done that enough that we should know that by now. It's always going to give us the same value when the confidence level is 0.99, 2.58. All right, so that's number 6. Let's take a look at number 8. Number 8 says we have 95% confidence, n is equal to 40, sigma is unknown, and the population appears to be skewed. All right, once I see here that sigma is unknown, automatically the z-score, the critical z value is out. We can't use the z because we don't know sigma. You can only use z when sigma is known. Well, let me see the other criteria. If I want to use the t distribution, it has to be a simple random sample, which again we assume, but it also has to meet one of the two conditions. Either the sample size is large enough or the population is normally distributed. Well, this population is not normally distributed because it says it appears to be skewed. The normal distribution is a symmetric distribution. It's not skewed to the left or to the right. So it's not normally distributed. So our only hope for using the t distribution is if the sample size is large enough. And in this case, we do have a sample size larger than 30. So the t distribution is okay because we have a sample size of 40. So we can use the t distribution here. So we're going to be looking for the t of alpha over 2. Well, let's go ahead and find alpha over 2, and then look at table A3 to find the t score. Well, alpha is 1 minus the confidence level. Here, the confidence level is equal to 95%, which is 0.95. So alpha is actually equal to 1 minus 0.95, which is 0.05, 0.05. So alpha over 2 is what we actually need, because we're going to be looking for the t-score that has alpha over 2 in the right tail. So the t-score, alpha over 2 is 0.05 over 2, or 0.025. And what we're going to do is we're going to look at table A3, and we're going to look for the t-score for 0.025 in one tail. And that's going to be our critical t. So let's go up here to table 8.3. So here's table 8.3. Oh, the other thing we need to know, I forgot to use that table, is the number of degrees of freedom, actually. So our degrees of freedom here, our degrees of freedom, are going to be n minus 1. Well, n minus 1. And in this case, that's 40, which is n, minus 1. So our degrees of freedom are 39. We need that information to use table A3. So the information we need to know how much area we have in one tail. The area in one tail is 0.025 alpha over 2 is the area that we need in one tail. And the degrees of freedom are 39. So let's go back up to table A3, and we are going to find that, let's see here. we're going to find the degrees of freedom are equal to 39. So we look for 39 degrees of freedom. 39 degrees of freedom is right here. So this is the row that has our 39 degrees of freedom. So we're looking above that line. And above that line, we're looking at the row above that line. And what we need is we need the area in one tail to be alpha over 2 or 0.025. So here we have the area in one tail in this top row, and we want that area in one tail to be 0.025. So it's this middle column. So I'm looking at this middle column and the row above that line, and I'm looking for that score right there, which looks to be, let's see here, that score right there, the critical T is 2.023. So in this case, this problem here, we get the T score, the critical T to be 2.023. So that's the answer that we get for number 8. Number 8 is 2.023. We needed degrees of freedom, and we also needed the area in the tail to get that. All right. So let's go ahead and do number 10. Number 10. Well, oh, this thing is acting really quirky. All right. Let's go ahead and do number 10. So for number 10, let's see. Number 10, we have a confidence level of 95. A confidence level of 95. So the T of alpha over 2 is not going to be the same number unless we have the same um, sample size. So we can't assume that because it's 95% confidence, we're using this T of alpha over 2, this critical value. But let's see if we can use this critical value at all. Well, let's see. N is equal to 9, sigma is unknown, and the population appears very skewed. Let's go through and use that flowchart to see if we can use any of the methods of this section. The first thing, we do go to the start here. So on the start, from the start, we're going to follow this flowchart down, and it's going to ask us a question. Is sigma known? Well, is sigma known? Well, we can answer that question. If we take a look down here at number 10, it says sigma is unknown. So we can answer this question, is sigma known? We can answer that question, no. So we're going to go in this direction. We answer that question, no. Then they ask us another question. Is the population normally distributed? Well, let's see the answer to that. Down here it says, the population appears to be very skewed. If the population is very skewed, it's not normally distributed. So the answer to the answer to that question, is the population normally distributed, is also no. So we're going to answer no to this. And then it asks us, is n greater than 30? And let's see, is n greater than 30? We're taking a look down here. N is equal to 9. So the answer to that one is also no. So we've answered all our questions no, and it says use non-parametric or bootstrapping methods, which means we can't use Z or T. So in this case, we can't use any of the methods from this section. We can't use Z and we can't use T. So the answer is C. State neither the normal nor the T distribution applies. So neither the normal nor P applies. So none of those distributions apply. All right, let's look at this last one. All right, we have a 95% confidence level. N is equal to 38. Sigma is unknown, and the population appears to be very skewed. So let's see. It says here the population also appears to be very skewed, but let's see if we can apply any of the methods from this section. So let's go back up here. Let's erase this guy. Let's see here. Let's start here. So from the start, it says, go down here. We have a question. Is sigma known? Well, let's see. For number 12, it says sigma is unknown. So I answer that question, no. No, sigma is not known. The second one, is the population normally distributed? In this case, it says the population appears to be skewed. Population. So the answer to that is also no. Oops, I keep doing that. The answer to that is also no. So we answer this question, is the population normally distributed? No. And the last question, is n greater than 30? Well, let's see n. Our n is 38. So the answer to this question is n is greater than 30. The answer is yes. So in this case, t distribution can be used. So we can use the t distribution. So we're going to once again find a critical t value. To find a critical t value, we use table A3. So in order to do that, we need to know alpha over 2, and we also need to know the degrees of freedom. So let's find those. So let's see. Alpha is 1 minus our confidence level. So alpha is 1 minus the confidence level, which is 1 minus 0.95, which is 0.05, 0.05. And alpha over 2 then, alpha over 2 is equal to half of that, 0.025. The degrees of freedom are equal to n minus 1, which in our case is 38 minus 1, 38 minus, oops, 38, and we're subtracting from it 1, 38 minus 1, which is 37. So we have 37 degrees of freedom, and those are the two pieces of information we need in order to use the t distribution. So we have 37 degrees of freedom, and alpha over 2 is 0.025. So we go back up to table A3. Let's get rid of what we did before. Table A3 is here. And what we're going to do is we're going to look for the degrees of freedom to equal 37, and we're going to look for our area in one tail to be 0.025 again. So once again, we're in this middle column because we had the same confidence level. But now we're looking at the row that has 37 degrees of freedom. So what we're doing is we're looking at the row that has 37 degrees of freedom, this row right here, and we're looking at the middle column. So we're pulling off this value right here. And why that value? Well, if we look above, this is the column that has area in one tail of 0.025. That is our alpha over 2. So we find alpha over 2 in that top row. We find the degree of freedom along the first column, and the intersection of that row and that column will give us our critical z, 2.026. So the critical t here, critical t is 2.026. So here, the t of alpha over 2 is equal to 2.026. And there we've done some problems where we're calculating the critical t. All right, now let's put this all together and see how we can use our calculator actually to calculate the entire confidence interval like we've done before. So those are all the steps that would be involved. Actually, before we do that, once again, let's go ahead and do the confidence interval by hand for one of these. All right, if we're going to do, actually we can't because we don't know X bar. So let's go ahead and do this. So the Atkins weight loss program. In a test of Atkins weight loss program, 40 individuals participate in a randomized trial with overweight adults. After 12 months, the mean weight loss was found to be 2.1 pounds with a standard deviation of 4.8 pounds. So you notice here that when they gave those numbers, they said that we have 40 individuals, and for these 40 individuals, after 12 months, the mean for those 40 individuals is 2.1 pounds, and the standard deviation for those 40 individuals is 4.8. So we do not have a population standard deviation, sigma. This standard deviation, 4.8, is actually the standard deviation from those 40 people. So we can't call that a population standard deviation. That is S, not sigma. So they didn't explicitly tell us that this was the population standard deviation. And actually, if you read the question, it implies that this is only the standard deviation for those 40 individuals. That's really the only way of telling the difference. It's the English behind this sentence. It says these 40 individuals with a mean of 2.1 and a standard deviation of 4.8. So you can assume that they're referring back to those 40 individuals. So now we have S to be 4.8 pounds. And let's see what else we have. We also have the mean for those 40 individuals, which is X bar. The sample mean is 2.1 pounds. So those are, oh, and we also have the sample size. There are 40 overweight individuals. So 40. So part A says, what is the best point estimate of the mean weight loss of all overweight adults who follow the Atkins program? Well, we're trying to calculate the mean weight loss, which is mu, but the best point estimate for mu is always x bar. So the answer for part A is x bar. The sample mean is the best estimate, best point estimate for the population mean. So part A is 2.1. Part B, construct a 99% confidence interval estimate of the mean weight loss for all such subjects. So now we're going to create a confidence interval. All right, to do this, we're actually going to use our TI 83 plus calculator. And this is what we're going to do here. Well, first we turn it on. Let's clear it. And what we want to do is, before when we were doing confidence intervals, we did the same thing. We went to stat, then we went over to tests. So we scroll over to tests. And once we went over to test, well, first for the one proportion, for this estimating this population proportion, we went to one prop z int, one proportion z interval. Then the next time we did it, we only went to z-interval because we were estimating a mean. But we don't have a z-interval anymore because we're not using a z-score. Right under z-interval, number 8, you'll see is t-interval. So in this section, if you do not know sigma, you're not going to use the z-interval, number 7. You're going to use the t-interval, which is number 8. And if you notice, when you press enter, it already has statistics highlighted. When we did the z-interval, it asked us for sigma because it assumed that we knew sigma. But in this case, it's asking us for S, the sample standard deviation. And once again, if you don't clear it out, it still has the information that you have the last time you did an interval. So let's go to X bar. X bar in our case is 2.1. So we plug in 2.1 for X bar. The sample standard deviation, S, is 4.8. N is 40. Oh, it's the same as in the last example we did apparently. And the confidence level, we want a 99% confidence level. So I'm going to put 0.99 for my C level or confidence level. Then I hit calculate. And it thinks for a while, and then it gives me this interval. All right, so the confidence interval we've created starts at 0.04484. So that's 0.04484 and ends at 4.1552. All right, so that's part B. Construct a 99% confidence interval estimate. This is the confidence interval. The lower limit is this, the upper limit is this. And then part C. Part C is the interpretation. Does the Atkins program appear to be effective? And is it practical? Well, it does appear to be effective, and let me explain to you. You see, this confidence interval that we've created does not contain 0. So it seems as though if we were to use this confidence interval to determine whether or not you would actually lose weight, it would say that since 0 is not on this interval, then 0 is not we're 99% sure that 0 is not the population mean for weight loss. So if the population mean for weight loss on the Atkins diet is not 0, it means that you actually lose weight when you do the Atkins diet. But now, is it practical? Well, it seems to me like you're only going to lose somewhere between this many pounds and this many pounds. So if you're only trying to lose 4 pounds, then yes, it's practical. But if you're not trying to lose more than 4 pounds, it seems a little impractical. I think we'd want our confidence interval to be a little bit further to the right if we actually consider this to be a practical diet. So for part C, does the Atkins diet appear to be effective? The answer is yes. And the reason is the confidence interval does not contain 0. And for part B, well, that's a matter of opinion.